All right, so we're going to look at how to graph these functions. And so the first skill we want to look at are what kind of functions should we know at this particular point. And maybe if we don't know them, then we will definitely find them. So the first one is our basic linear function. It's f of x equals x. This is in fact a straight line. Okay. And looking at our line here, we can see a couple of key points, 0, 0, 1, 1, 2, 2, kind of goes through there. So I can make a table of values then. So negative 2, negative 1, 0, 1, and 2. Okay. And I think it's fair game to kind of mention that we should at least, whenever we're identifying graphs, we should at least label those middle key points in the graph somehow, some way. Our next function is the quadratic. This is what you might hear called a parabola or squared function, another name you might hear it called by. And so you can see in this graph that it goes through 0, 0, goes through 1, 1, negative 1, 1, it goes through 2, 4, and negative 2, 4. So let me kind of write these down. And again, I think it's reasonable that we would not just know the main critical points in the center, but understand the curve shape that is generated when we graph it. All right, our next function is the root function or square root or radical. Kind of looks like all of them have sort of the general curve where there's a starting point and it kind of arches up like a rocket being blasted out. Looking for critical points there, and this is where we got to realize we're dealing with the square root function. So it's whenever we look for main points to plot, we want to pick numbers that are easy to square root. So something like 0, we get 0. We get 1, square root of 1 is 1. 2 and 3 aren't so pretty, but 4, on the other hand, square root of 4 happens to be 2. So, but when you're plotting the square root function, then I would expect at least 0 and 1 to show up. And sometimes it helps if you put the 4, 2 in there, but continuing on. Okay, absolute value or the V shape. You'll hear what it looks like and key points. You can see it goes through 0, 0, 1, 1, and negative 1, 1, 2, 2, and negative 2, 2. But it is V-shaped. And it's kind of the same critical or key points as the quadratic, but with the quadratic we understand there's a curve to it. This time we expect it to be just a straight V shape. Okay, next up is the cubic function. Cubic functions sort of have this S-looking shape to it. It's kind of an easy way to recognize them. It also goes through 0, 0, 1, 1, from negative 1, 1. Now this is off the screen here, but it would go through 2, 8, and negative 2, negative 8. Sorry, I need to make those negative. So the critical points there kind of look familiar as the other ones, as far as what things you would want to manipulate in order to get the cubic function to show up. Now we're looking at the cubed root function. So if the cubed function kind of looks like a vertical S, this one looks like a horizontal S. Sort of does that feel about it? And again, you can see through the graph that it goes through 0, 0. It also goes through 1, 1, and negative 1, negative 1. But again, the curvature here is horizontally the line. It's going from left to right instead of up and down. But again, if you think about it, there's sort of a connection between a cubed function and a cubed root function. So cubed is vertically aligned, cubed root is horizontally aligned. So now that we have a basic understanding of the parent graphs that we are allowed to manipulate, let's take a look at characteristics of the equation and what it physically does when we manipulate these numbers. So the first thing that we're going to address is the number on the outside. So let's say I take a function and I'm either adding or subtracting it. What does that do? Well, when we add a constant to the function, this shifts the graph up that number of units. So if it's a plus 5, everything goes up 5. When we subtract a constant from the function, then the graph shifts down k number of units. Okay, so visually, let's kind of go in here and take a look at this. Let's start with, we're dealing with the absolute value. So if you remember, it goes through 0, 0, 1, 1, and negative 1, 1. And so I can kind of draw in that. So we're going to do that in black. Okay. Absolute value of x plus 2. So I'm going to do this one in red. That means everything got shifted up 2. So instead of going through 0, 0, it should go through 0, 2. And I can add 2 to each of these points and generate the new image. That's what happens. And then same thing with, we'll make the blue one the minus 3. So instead of going through 0, 0, it got shifted down 3. And I can count all of those points to see which one got shifted down 3. Okay, sort of another way to think about this is if I look at the parent graph of negative 1, 1, 0, 0, and 1, 1, right? When I look at, say, the absolute value of x minus 3, what does that do? Well, that takes every ordered pair and it subtracts 3 from the y's. So I can go into each of my points and I can go, well, from negative 1, so the negative 1, 0, and the 1, the x's stay the same. All the y values for those same points are going to go down 3 units. So 1 minus 3 puts it at negative 2. 0 minus 3 puts it at negative 3. 1 minus 3 puts it at negative 2 again. Okay, so we can kind of use a mapping idea to also visually see what's going on here. Let's take a look at the next one. Here we got x squared for our parent, and the critical points there is that it goes through 0, 0, 1, 1, and negative 1, 1. But again, there's a curve to it. If I shift up 3 units, instead of being through 0, 0, it's going to go up to 3, 0. But it's also going to go, all those other points are going to go up 3. And it's going to have the same sort of curvature to it. And lastly, minus 5. So if I go down 5 units from 0, 0, and then take the other 2 points and move them, I should get the other image. And again, I'll just model it with this last one. So with that x minus 5, what that does is that takes all of our y values and subtracts 5 from them. So if the parent graph, our main critical points would be those 3 points. So then the transformation one, the x's would stay the same, and the y's I would just subtract 5 from. So negative 4, 0 minus 5 is negative 5, 1 minus 5 is negative 4. And those 3 points are the ones that I should have labeled in that picture with the black quadratic. All right, our next transformation is horizontal shifting. And this is if we're adding or subtracting inside the function. So you can kind of see down below we've got examples of that. You notice we're adding 1 here and subtracting 3 to the square root, as opposed to on the outside of the function where it moves it up and down. If it's inside, this actually moves it left and right. Now, it is kind of backwards of what we might imagine. So if we add a constant to the x, the graph actually shifts to the left that number of units. Normally we think of left as going more positive and going more to the right side, but it actually goes to the left. If I subtract a constant from x, that actually makes it move to the right. Okay, so again, it's a little bit of backwards from what we might imagine. So I always like to make this note that this is backwards of what we see. I see a +1. I'm actually going to move -1 in the x direction. But at least it's consistent. So let's go through these 3 graphs here. Here we got the square root of x. Square root of x, if you remember, has the ordered pairs 0, 0, 1, 1, and 4, 2. So 0, 0, 1, 1, and 4, 2 looks about like that. So we'll kind of put it in black there. Alright, so we'll do red with this one. The +1 says don't move it in +1, but move it -1. And then take each of my points and move them back 1 unit. It's kind of hard to see there. It's kind of hugging very close. I'll do this one in blue, and that's the one I'll show the mapping on. So the blue one says square root of x minus 3, so instead of being at 0, 0, we're going to move it over 3 units, and then all of my points are going to move over 3 as well. Okay, so that's what that looks like. And again, if you think about the transformation, what that's doing is it's changing the x's, and this is again where it's opposite. Even though it says -3 inside the square root, we're actually going to add 3 to each of those numbers. So this time the y values stay the same from the parent graph, but the x values we all add 3 to. So 0 plus 3 gives us 3. 1 plus 3 gives us 4. 4 plus 3 gives us 7. And those should be the 3 points that I ended up plotting in my graph. Okay, so you can either count and then you can see where the ordered pairs are, or if you want to use this mapping idea, also kind of helps us visualize that. Alright, so let's jump to our cubic here. Cubic has got the critical points of -1, 1, 0, 0, and 1, 1. And it's that vertically aligned S shape. Looks about like that. Sorry, I should label this up here. So we're going to do green there. Here I'm going to go with gray. And the +3 says not move 3 to the left, but not move 3 to the right, but move 3 to the left. So it's going to come back here to -3. It'll be that first point. This one will come back to -2, and that'll come down to -4. And then I just follow the curve. Okay, so this next one is a little more complicated because we got 2 different transformations going on. I'm got a -2, which means I'm going to move over 2, but I've also got a +4, which means I'm going to move up 4. So for each of my points, I want to move 2 to the right and 4 up. And then I want to draw in the sketch from there. Now, the nice thing is, if we look at what the mapping does, we can see numerically what's happening to each of our ordered pairs. So here I want to add, let's see, x's we're going to add 2, and the y's we want to add 4. And so when I look at the ordered pairs, if I go back over here, so -1 plus 2 gives me 1, 0 plus 2 gives me 2, And 1 plus 2 gives me 3. And then I'll do the same thing to the y's. 1 plus 4, I get a 5 out of that. 0 plus 4, I get 4. And 1 plus 4, I get 5. And so, you can, oh, I'm sorry, my points were wrong. That should be a -1. That's, I mean, picture's still good. That's just going to change this one number. See, -1 plus 4 puts us at 3, which that's what that matches. So if I look carefully, I should have an ordered pair at 1, 3, which I do. Then I should have 1 at 2, 4, and 3, 5. Okay, so I notice I'm moving it over, and then I'm using the transformation, the mapping changes to come up with the new ordered pairs as well.